Welcome to Calc 3. This is section 14.6, surface integrals over vector fields. So one thing to note is that you can take the mass of an object, if you have its density over a surface, you can write that as the double integral of the surface of the density function ds, as if you take that domain, where you take that surface and you rewrite that surface as you parameterize that surface in terms of a value r, where it has two inputs, r of u and v, describing that surface. You can parameterize the change in that surface as the magnitude of RU cross RV dA with that over that domain D. So if you're given a problem where you're finding the mass, this is an example where you can use that density function here to calculate the surface integral. Now, if you're looking for the surface integral over a vector field, to calculate the flux, for example, you can do a very similar function of this. So here f is your vector field, and r parameterizes your surface in terms of two variables, and ru and rv are the derivatives with respect to u and v and those particular functions. So the flux is the same over a surface, is the same as taking the vector field parameterized by that surface, dotted with the surface itself in the pieces. So let's look at an example here. So let's let S be the plane z equals f of xy equals 8 minus x minus y over the triangular region with vertices 0, 0, 1, 0, and 1, 5. 0, 0, 1, 0, and 1, 5. With vector field f is 3, 1, 2. So this is a vector field that doesn't vary with respect to x, y, or z. And we're asked to find the flux over the surface. So we can think of this in 5 steps. So the first thing we want to do is we want to find r of u and v. We want to parameterize that surface in terms of two variables. So you can think of the surface as, if we let x be x, y be y, and z be 8 minus x minus y. You can also write this in terms of u and v. You can say this is u, v, 8 minus u minus v. So now we found our r function. The second thing is to take its partial derivatives. So r of u, we can say is 1, 0, negative 1. R sub v is equal to 0, 1, negative 1. And then we need to make our third case, our third step here, is f as a function of r. Since f is a constant vector field, we are left with f as itself, but if f had x, y, or z inside of its vector field, we would substitute in the parameterization of r. Fourth, we look at our region. So given our region here, we go from 0, 0 to 1, 0 to 1, 5. So we need to decide how to describe this region in terms of rectangles. So this is our u-axis and our v-axis corresponding to our x and our y. So our u is an element of 0 to 1, and our v is an element of 0 to 5u, if we think about what this line here looks like. This is the line v equals 5u. So as we look at this, so we've parameterized our region. So now we just calculate our flux. So the integral of our flux, f n ds over the surface S, this is equal to the double integral over our region of f evaluated at r, dotted with the cross product ru, rv, with respect to the area, which when we calculated ru, rv, this implies that the cross product ru cross rv is equal to 1, 1, 1 in this case. So then our flux is equal to the integral from 0 to 1, 0 to 5u of 3 plus 1 plus 2 dv du, which is the integral from 0 to 1, 0 to 5u of 6 dv du, and this is an easy integral to solve, and so we get 15 as the flux across that surface. Let's do another example where S is a unit sphere and F is this vector field y minus z, comma z minus x, comma x minus y. We're finding the flux over S. So we could parameterize the surface, but let's also note that our sphere, we can describe our unit sphere as a function x, y, and z is x squared plus y squared plus z squared minus 1 equals 0. Our unit sphere is x squared plus y squared plus z squared equals 1. So we can think of this as also the gradient of f is equal to 2x, 2y, 2z. And recalling back from earlier in the semester, the normal vector is a gradient of f divided by the magnitude of that vector. So when we're doing this, we're evaluating f over s, the flux over s, ds. We can think of this f dot n ds. We can think of this as over the domain d of f dot grad f, our normal vector here is given by grad f over the norm of grad f times the norm of grad f dA. So this is another formulation here where this is ds and this is our normal vector n. So what we see is this cancels out, and so our normal of the grad vector cancels out, so we're left with f dot grad f, grad little f dA. And so we get over our domain, whatever that happens to be, we haven't calculated that yet, of y minus z, z minus x, x minus y. Let's move this integral down, dotted with 2x, 2y, 2z dA. This gives us our flux. So doing out the dot product, so over our domain, we get 2xy minus 2xz plus 2yz minus 2xy plus 2xz minus 2yz dA. That inside of the integrand there is equal to 0. So therefore, our flux in general is equal to 0 over the unit sphere with that particular vector field. So as always, if you have any questions, let me know.